I will talk about elasto-plasticity driven by dislocation movement, which is joint work with a couple of people, as you will see on the slides, and it's been kind of a long-going story to, at least for me, to try to figure out some ways to destroy it, and kind of couple microscopic questions of dislocation motion with the macroscopic theory of kind of deformation of plastic solids. So I understand I am talking to a very specialized crowd, but I thought I'd start with some very gentle overview of what it is we're doing, if only to fix notation and terminology. So in a few words, let's say you have given some reference configurations for some piece of material, and this bit material can be deformed plastically. You see this thing has been bent by a deformation. You obtain a deformed configuration. And if you look at microscopically what's going on, you will, so here's a crystal lattice, and let's say this corresponds to the undeformed lattice. And you have the deformed lattice where you can see these top two rows of atoms have been shifted to the right. Now, of course, if you shift them, I mean, you should think about a bit more how exactly that comes about. Because so the first kind of naive idea would be to cut all of those bonds and then shift everything to the right a little bit. Yeah, so everything moves by one atomic distance. But if that turned out to be what's really happening, then the strength of materials would be way too strong for you to bend, like say, metal with your hand. Yeah, so you couldn't bend the spoon somehow, except I think I gave a talk about this once, and someone said, yes, but except for Uri Geller, with the mental bending of the spoon. So, except for paranormal activity, you wouldn't be able to bend the spoon. And, okay, so that's the kind of picture. So what really happens in real crystals is that they are not perfect. So they have these defects. So here you have a line defect, which is called a dislocation. And so you see you have fewer lattice columns at the bottom than you have at the top. And then what's a more efficient way of moving here is by just cutting this row of bonds and then kind of flipping them over to that side. And then so you see the dislocation has effectively moved one lattice spacing to the right. And if you keep doing this like some sort of caterpillar moves, you end up with having shifted the top bit of the crystal by roughly one lattice space. So obviously you have huge numbers of these dislocations in real materials. They kind of move through them. So this is basically why plastic materials deform as they do. And so when you, in a crystal, say you're looking at it somehow locally, how can you detect such a crystal, such a dislocation? Well, one thing you can do is you can just go around with some sort of circuit and count how many bonds you cross with kind of the direction of the crossing, and you see if you do this, you sum to 0. But if you do it on this side, you have kind of more on the top, so you cross more like that, so you kind of end up with a net charge. And this is called the Burgers charge, or the topological charge, or somewhat of the displacement associated with the dislocation. And I want to make a few remarks, because obviously this talk is about how to represent such phenomena mathematically and how to kind of put them into a framework that we can do analysis with. So the first thing you can think of as these dislocations, as you can abstract them to one-dimensional oriented lines in some three-dimensional domain. And one point I want to make is, maybe for material scientists this is not such a big deal, but for people who come from more geometric analysis or geometric measure theory, this is codimension 2. What do I mean by this? It means we have 3 dimensions here and 1 dimension here, so there's 2 in between. Yeah? And in geometric analysis, the codimension 1 case, so if you have 1 dimension between your object and your ambient space, is always easier, roughly speaking, than the codimension 2 case. So we really have to kind of think of codimension 2 from the beginning. And then the second point is, for effectively atomistic reasons, these loops are closed within a crystal. If it's a single crystal, if it's a polycrystal, this applies within a grain, up to a grain boundary. But at this point, I'm only talking about single crystals. Okay, and yeah, as I already said, that the Burgers vector is kind of the stacking fault around the dislocation line. But there's some sort of more dynamic interpretation of it. namely that when these things move, so the Burgers vector maybe would point, I don't know, to the right or to the left, depending on how you want to set up the signs. And then when it moves, it also gives you the net displacement of kind of the top versus the bottom. Yeah, so it's not, it has this interpretation as in terms of this Burgers loop, but it also has this interpretation dynamically of what it does to the crystal. So if you want, that's the linking between the microscopic line and the macroscopic effect it has when it moves. and so for this talk, just to keep notation simple, because otherwise we end up with some sort of additional layer of notation, there's only one Burgers vector. It has nothing to do with the actual works. They don't care as long as it's a finite set of Burgers vectors. But I want to just fix it for one here, because otherwise I have to index every quantity by the Burgers vectors, which I want to avoid. Okay, and I want to say, look, I mean, lots of people have worked on this, obviously. Here's some names. Some of them are in the audience. Some of them are not in the audience. A lot of people have worked on this in many different ways and with many different angles, and it's difficult to kind of join all of those dots together. But I just want to say that a huge number of people have invested significant amount of energy into understanding this. Right. Okay, and so as you could already see from the title, I'm actually interested not so much in the static case, where quite a lot is known in different avenues, but I'm interested in the evolutionary case. So I want to really understand what happens when these dislocation lines kind of move about in the crystal and do something to the deformation. Okay, and so here you could see this would be one loop. As I say, I've abstracted now to a loop away from these kind of very discrete lines. And when you try to do this, you have to ask yourself a couple of questions that you need to give some sort of answer to, hopefully a realistic one in terms of material science. So the first question is, which of those evolution can be stood as deformation? I mean, this is not a particularly well-defined term, what a deformation of a loop is, but what I mean is that what you shouldn't be able to do is rip it apart and then kind of reconnect it in some weird way. I mean, these things don't do that. They should have some sort of, if you want, that's a regularity question of these evolutions. Then the other thing is that you do really see topological change. So for instance, here you see this loop shrinking to a point and then kind of disappearing, or it could actually be nucleated from a point and come out, assuming that there's enough nucleation sites and so on. And they could intersect and they could kind of go through each other and pinch off smaller loops and also on. So there's a lot of like very complex phenomena which would be quite good to be representable. And then, so when you try to put some energetics onto this, the other thing you need to do is, I mean, this movement doesn't come for free. Of course, if I move them, I'm still cutting my bonds in my crystal, so that costs me energy, some activation energy to cut that bond, and then I get the energy back, but of course I radiate away some heat effectively for the movement. And so I need to count kind of how much have I moved? I mean, what's the energy dissipated? And so you can think of this roughly in first approximation. It's only a first approximation, but it's not too bad. As the area that you have traversed, yeah. So if your loop traverses a certain area, there's this shaded region here. That's kind of roughly proportional to the energy dissipated. Yes.
And that has me question perhaps. So the topological regime, what's preserved in the word topological, so there perhaps a topological invariance even under these.
Yeah. So the Burgers vector is kind of constant along the loop. That stays the same.
So thinking of this singularity case you were mentioning in the middle.
It disappears. Well, that's nucleation and destruction of dislocation, yeah. I mean, it affects, of course, the movement. So, I mean, the point is that while it moves, it will certainly affect will have an effect on it, but then, of course, these things can be destroyed or can become bigger. But, of course, it costs energy. I mean, it's not like it gets destroyed and then somehow there's some sort of energy loss. I mean, the topological charge in that sense is not preserved. Okay. Anyway, but there's one issue here. I mean, I would like to already make clear here that if you kind of go backwards and forwards, you're kind of traversing an area twice. Yeah, so you need to. I mean, you cannot just go back. It's not a reversible motion in an energetic sense. So if I go over there, and then I go back, that cost I have expended energy for moving twice, right? I mean, it's not like I've just kind of got I'm not a potential energy system. Somehow I don't kind of get the energy back. This is fairly level. So it's just friction. Okay, and then also, this is more of a technical point. When you look at these kind of evolutions, you would kind of like to define a velocity of movement, because the velocity will then feed into the other equations of this driving force. And yeah, and then finally, of course, being an analyst, I need to also think about, of course, if I want to construct anything, I'll probably have some form of approximate solutions. I have to pass to some limit in some topology, so I need some sort of topology for these evolutions. Okay, and so how can we solve this, or how can we do this? I mean, before I go on, maybe I should make a general remark. So I really want to focus on the question of representing these issues and these evolutions in a mathematical framework. I mean, we all kind of agree what the microscopic rules and laws are for movement and what kind of the energetics should be. But I mean, that is some sort of very microscopic view. We need to tie this all together into a framework that allows us to kind of do analysis on it. That's the topic of this talk. Okay, and so for this, I'm going to use something that is very, very well known, I suppose, in the community of geometric measure theory, and these are integral currents. So you can think of integral currents as generalizations of manifolds, of oriented manifolds, in a measure theoretic way. That's in a nutshell. But the definition is slightly involved, so let me give you one slide here to maybe refresh everyone's memory. Or, I mean, I understand this is a diverse audience, so I'll try to explain. But if you don't want to think about the technical details, think of them as being effectively manifolds. So, okay. So the idea is to first look at the space of smooth, compactly supported K differential forms, and then the currents are effectively the dual space in some topology. And I care about this particular subclass of currents. First are the integer multiplicity rectifiable ones, which are given as really, a surface measure on a rectifiable set, which is called the area set, which is HK rectifiable, times the orienting vector. So in the case of a 2 surface, this is a 2 vector. I mean, in 2 surface in R3, you can also get away with parametrizing it by the normal. However, I'm going to talk about 2 surface in R4 in a minute, so then that's not so clear anymore, because you would have 2 normals. And I'd rather have 2 vectors, a 2 vector, than 2 different normals, because that's actually more confusing. So, and then you have a multiplicity, so in principle, if it's just one sheet, thinking of multiplicity just being constant equal to 1, but maybe it's kind of 2 in when you overlap. And then if you do this, you can get the mass, which is the volume or the area, depending on what K is. And one very nice thing of this kind of general framework is that you can always define a boundary. And so the boundary is defined as this is the adjoint to the exterior differential of forms. You can see this here. But for the integer multiplicity currents, it really is kind of the topological boundary of this rectifiable set. Let's say this rectifiable set is nice. So C1, say, then you see this is in blue here with the induced boundary orientation. Yeah, so the induced boundary orientation is defined at some point in differential geometry, and it's some sort of depending on you see it's one direction here and the other direction on the other side. Okay, and then integral K currents are just defined as those integer multiplicity rectifiable K currents whose boundary is also integer multiplicity rectifiable. In fact, you can delete this here because if you have finite mass and finite boundary mass, that will imply that the boundary is rectifiable. That's one of the fundamental theorems of this theory. Okay, and then I also define this space here where the support is restricted to a set. Okay, I mean, so if this is just, it's a nice class, I should say, from an analysis point of view. It has some nice compactness properties and a lot of theory that I'm sure everybody has read Federer's great book. You don't have to say say too much about this. It says a lot about the audience that you get this joke right away. Okay, and so the idea now to apply this theory to my problem of describing dislocation motion is the following. It's a very simple idea, but it seems to have a lot of ramifications. So the first is that we actually don't look at some sort of the dislocation loops individually indexed by time, but I'm looking at the surface traced out by them. So we get a two-dimensional surface in the space-time cylinder 0t cross omega bar. So it's really, we're looking at the whole surface, not just the thing. And okay, this is some sort of fairly simple paradigm if you want, but it seems to work out quite well for what we want to do. So the first thing is, how do we get the dislocations back? Well, there's a nice operation called the slicing, which really you can think of as intersecting of this surface with a hyperplane at a fixed time, and then kind of looking at the trace that this surface makes on that hyperplane. And then I also need to do one more thing. So I want to push forward under the spatial projection, which takes t and x and just gives me x. That just forgets the t component, right? Because I don't kind of want to have that. So I just get rid of it. And so then I end up with s of t, which is really this dislocation at time t. Now, the nice thing is I told you that all these things, these loops have to be boundaryless, and you can easily prescribe that for the surface, namely the surface can have only boundary at the beginning and the end point. Then one can prove that all these slices are boundaryless. Okay, and I should say I'm going to switch to doing this more general as for K currents, and then we're looking at these trajectories, which as in S1 plus K in the space-time cylinder. I mean, it's just that here it makes no difference at this level, but for dislocations, K is 1. And so one kind of advantage of this approach is that for the surface, you can very easily define a variation. And so this is the formula. So you take the projection of this orienting vector. Remember, this is a 2 vector or a 1 plus K vector. And the projection here can be defined by pulling apart this wedge product. And then I take the modulus and integrate it over the thing, and I get something that's a variation. That turns out to be precisely the area with absolute multiplicity. Let me say, if you were individually looking at the slices, so you're looking at a collection of kind of loops, it's actually not so clear how to define this. It's not always clear. You can glue them together into a surface and then define the variation. So really, this variation is precisely this area. But here I've got a more complicated thing. So I'm going here and then go back, and you actually, the variation, I mean, counts this part of the traversed area twice, because I'm going up and then down. This area once, so it has some sort of more complicated structure. And this is counted correctly by this expression. And in dislocation theory, as I said, the dissipation is roughly the variation. It's not entirely true, because kind of depends a bit on what reference and the formed frame, but I think this roughly counts the number of bonds cut. Okay, and so one other thing I want to mention is that there's some sort of nice mass estimate of the variation with respect to the mass of the current. And so the mass dominates the variation. That makes sense, because kind of total area dominates the component of the area in kind of projected onto one side. But it also goes the other way around. If I assume a bound, like an L infinity bound on the mass of the slices, so you can estimate them by each other. And another nice thing, okay, so if I say variation, the first thing we should check is that it's invariant. There's some time rescalings, right? Because the defining feature of the variation is that if I reparameterize my time, it shouldn't change. And this is true. I mean, you can prove this, that if you take any Lipschitz rescaling of the time interval, the variation doesn't change in this form. Okay, so maybe I should give one kind of example to show what this is, so that you could believe me that this is nothing too dangerous. So if you take any kind of BV function, you fill in the jump, and now you take the current on the graph. So a bit like what studying the theory of Cartesian currents. So this is the graph, and now if let's compute. I claim that the variation in my sense, is equal to the classical variation is equal to the total variation measure of this here. So I mean, nothing happens. So let's compute just as a small exercise. So the variation of u is given as the integral over the u dot. Now, what I can do is I can transform this by the area formula as an integral over the graph, and I end up with this additional term here, right? So this is the measure, the area factor, if you want. Now, it turns out that P of tau is just, if you compute it, the modulus of this is precisely that thing here. Because u dot in direction, I mean, tau will have a component in direction t and one in direction up, and in direction x, it will be u dot. So you get precisely this here. And this is precisely my definition of variation. So I mean, the point is that this is some sort of higher dimensional analog in general of this. So it's not something totally strange, but it's defined just on the graph. It works. Okay, and so now I claimed that I can compute some velocity, which is useful. And so for this, I first need to introduce another class. So I want now Lipschitz regularity in time, because I said in the beginning I need some deformations. I mean, otherwise it's not so much, it's problematic to see what is a jump in time. I mean, the dislocation isn't just here and then it just jumps to a bigger one. That just doesn't happen. At least not if we rescale time in the correct way. And so let's say that the variation is Lipschitz. It's not exactly the right condition here. I mean, this is part of it, but you need to be a bit careful at the end. So, but let's just keep it as this roughly what it means. And so this is my trajectory. And the orienting map can always be written as psi wedge t vector. So t vector is the tangent to the loop at a given time. And psi is whatever is missing to make it into the correct 2 vector. But actually this psi from the general theory can be computed as some sort of R is the carrier set of this surface, and it can be computed as the R gradient of t. Maybe I didn't say what t was. So t is this projection which takes t and x and just gives me back t. So it's the time projection. And then divided by the R gradient of t. So this is this missing psi. And I mean, there's a general result telling you that the tangent space can always be orthogonally decomposed as the tangent space of these slices and this, whatever the span of this psi is. And now I define some sort of slit velocity or geometric derivative by just writing displacement per unit time. And the displacement in the x direction is p of psi divided by how much I've gone in the time direction is t of psi. And so I get an expression here. So this is really the slip velocity. So if you have a dislocation, you know, in the slightly more applied literature, people will talk about the velocity by which this thing moves about, and this is it. You can. The point I'm making here is just that you can compute it fairly easily from this kind of space-time approach. Okay, and what have I gained by doing this? So one thing I've gained, or one thing I am gaining here, is that I have a nice space of such evolutions. Yeah. I mean, the problem is when you look at time-indexed families of integral currents, it's kind of hard to make some sort of convergence theory, which we need if we want to prove some sort of theorem for them. And so here let me explain. The weak-star convergence for currents is defined by just pairing it with any differential form. So if you want to then having convergence for all of those pairings. But there's also like a geometric notion where you write Tj minus T as the boundary of some other current plus some current here. So Q is 1k plus 1 and R is k dimensional. And I mean, under a uniform mass bound, it turns out that these two notions are equivalent. I mean, you can think of this as the functional analysis version of convergence. This is some sort of geometric convergence where you fill in the distance between two currents with a surface. But they're the same if you have a uniform mass bound. Okay, and then, so what you get is, so there's a classical theorem called the Federer-Fleming compactness theorem telling you that if you have this uniform mass bound, there's a subsequence which converges weakly star or in this flat sense. That's a very powerful compactness theorem. So let me say, so that this is the non-trivial part here is not that you get convergence to some current in weak star sense. That would just be Banach-Alaoglu. The difficult part is that the limit is an integral current. Yeah, so the point is you could converge to something crazy. I mean, you could do some sort of oscillations, who knows what you converge to. But the point is, under this uniform mass bound, you converge something which is also representable by integration with respect to a Hausdorff measure. And that's actually quite hard to prove, I should say. I didn't, in my geometric measure theory course at Warwick, that's the one theorem I didn't manage to prove, unfortunately. Because, so let me prove it now. No. Okay, so what I want to say, though, as a consequence of it, is that you can now have some sort of weak star, BV weak star convergence, which augments this a little bit. So you have weak star convergence of these trajectories in integral currents of dimension 1 plus k, but you also have convergence of all the slices for almost every time. Okay, so it's like a pointwise convergence. And okay, so this I'm stating here, I mean, this is not a deep theorem or anything, but this is some sort of observation. If you have a uniform mass bound and uniform variation bound, you can actually get a subsequence which converges in this sense. Yeah, so you get also convergence of the slices. And in addition, if you actually assume this Lipschitz constant, this convergence of the slices improves to convergence at every t, not just almost every t, which is actually kind of neat because it tells you that really every slice is well defined somehow and convergence. Okay, and so now I come to something which is a slightly less trivial theorem, but it's extremely important for what I'm doing. And I call this the equivalence theorem, so it's just appeared actually. So, so the idea is the following. I have a bunch of these Lipschitz trajectories. So these are the space-time trajectories with some Lipschitz in time condition. And they have the following property. So the boundary of this Sj is delta 1 cross t minus delta naught cross tj. So this means that this here you can think of as tj. And, sorry, I'm reading it from the end up, which is not good. So I'm assuming I have Tj converging weakly star to T with that are boundaryless. And then I'm saying, well, actually, there is a sequence of Lipschitz trajectories transitioning Tj into T. So here's Tj and here's T. So what I'm saying is that I can take, I mean, I have weak star convergence, which a priori doesn't really tell me very much, right? Because it's some sort of weak star convergence, and maybe I can use the flat norm, so there's some surface in between. But it's not clear at all that this surface is some sort of continuous deformation. But what this theorem tells you that if you have weak star convergence, then asymptotically you can deform Tj into T with a trajectory. I mean, it's really a Lipschitz trajectory in time, which has vanishing variation. So the point is that I only have convergence, but now I can connect the converging bits to its limit. That's kind of the key here. And that's really important for the technical setup of what I'll talk about in the second part of the talk. Because I need to kind of weak star limits are not so useful. I need to kind of connect them. I need to have a motion that transforms Tj into T. And additionally, also, this kind of process doesn't mess up the slices. So the kind of supremum over the slice length is bounded by some sort of reasonable quantity. So it's not like I add some sort of crazy, like shrinking it all to zero in some way and then adding infinite amount of length there somehow. So I need to be a bit careful with that. So what I'm saying is I can translate this weak star convergence to zero into a slip trajectory. And the idea is a bit involved, but I have to get a new deformation theorem for integral currents and use some sort of homotopic deformation distance with respect to Lipschitz deformation. I don't want to go into the details, but the idea is that the message is you can translate this weak star convergence into a deformation. Okay. Right, so the second part of my talk is going to I want to talk a little bit more about the crystal lattice. Because so far, what I've told you about is how can we describe dislocation motion in isolation. I haven't mentioned plasticity again since the first slide. So I want to tie this up with plastic deformation and see what the effect is. Okay, and this is chaotic, so this slide perhaps, but so this is a picture from this work I did with Hudson, who was also at Warwick. Of course, the great irony of this is that I for once managed to collaborate with someone at Warwick, and then the pandemic hit, so we're still doing video conferences. Even though our offices are very close. So, so yeah, that wasn't too lucky there. Anyway, and so the idea here is now to tie this modeling assumption, and this description, the space-time currents, together with plastic deformation. Okay, and I want to let me do a modeling approach which is kind of similar to what has done also in the classical stuff, nonlinear, geometrically nonlinear elasto-plasticity. But I want to describe it in the following way. I don't want to say actually too much because I know that there will be C's talk in particular. I will also talk a little bit about how I can do this. So this in some ways actually closer to the geometric approach of Sima and Kupferman and so then it is to kind of make it. Okay, so the idea is that I want to, if I have this is my undistorted lattice and this is a distorted lattice, but what I've done here is I've actually kept the atoms in their place. I haven't moved them, they're pinned. Okay? What I have changed is I've changed the bond. So my plastic deformation has actually, what it has done is it has moved this bond, it cut it, and reconnected it to this one. Yeah? I haven't acted yet on the fact that this will, by some elastic relaxation, will of course mean that the top bit will shift to the left. Yeah? I haven't done that yet. I've pinned the atoms. So these I call the scaffold vectors, or we call the scaffold vectors, and these are the direction of the bonds between atoms in their reference position. And I put them into a matrix, and the matrix has determinant positive because I can't squeeze the things into the input plane. And then actually the classical plastic distortion turns out to be precisely the inverse of this matrix P, but maybe it's a bit kind of, I find it's a bit easier to argue from that side. And then what happens now I'm releasing the bond, the atoms, and so of course this thing, if no other force is present, will relax to some other situation, which are these ones. So I've called them by capital E. And so now of course you can say that the total deformation, this was what I was before in the reference configuration. So I'm mapping the vector Qi, which is this vector. I'm mapping, this vector here. This one will be mapped onto this vector. The effect of the gradient of the total deformation is precisely mapping Qi to Ei. And then, of course, if you mess around with this, you end up with E, the matrix being nabla Y times P minus 1, which is precisely your Koiner decomposition. Yeah, I mean, there's many different derivations of the Koiner decomposition for microscopic crystals. And I know there's a lot of work of Conti and Reiner and other people. But I mean, there's many different ways of justifying this. I just want to maybe also come up with we end up with the same thing, but the reason is it turns out later to be easier to prescribe a flow for the Q than for the P. Okay, and then if you have this, your elastic energy only depends on the elastic part of the deformation, so you get nabla Y times P minus 1. Yeah, which also, is the classical expression. Okay, and it's well known that if there are dislocations, then P is not curl-free. And if P is not curl-free, okay, roughly there's a bit of an issue here with inverses, and so roughly it means that I cannot compensate for P with this Y. Yeah, so if P was a gradient, curl-free, I could kind of think of it, at least roughly speaking, I'm not sure how much of this is a theorem, I could minimize out the gradient, and then I would be able to relax to 0. If this has curl, then I cannot do that, and that means my energy minimum is actually bounded away from 0. So it's like I cannot go to a fully relaxed state. which makes sense because I have these kind of dislocations which cannot fully elastically relax. Okay, but now I promised you some evolution. And so what happens? So one fairly straightforward way to describe it is that if I'm thinking about the bonds, well, what is the effect of a dislocation passing through a bond? Well, it cuts the bond and reconnects it to the lattice position next to it. That's a shear, yeah? I mean, it takes the thing and shears it to the right. So if you start from this, and B being your Burgers vector, which has to be in the so-called structural frame, so there's QB here, you get QI gets mapped to it becomes sheared. So this is an elementary shear over a plane with normal end. I'm shearing those things. So, okay, now I don't have just one dislocation, I've got many of them. So what's happened, Q at time t plus delta is kind of a shear here. Remember, I've got only one Burgers vector here. This is for the talk, yeah? I mean, just otherwise there's an integral over B or some sum over B. So let's ignore this because it's just more visual noise. In general, I have some sort of flux of dislocation. So if I have many of them going through, then of course this happens many times. And I end up with this equation here. So I integrate this flux from t to t plus delta. But now what I can do is I can just algebraically manipulate this. So what do I have here? Qt plus delta, the identity of Qt. So I get Qt plus delta minus Qt. Okay, that's divided by delta. And then I get this here on the right hand side, so I get minus Q, and on the right hand side, and now I put the Q on the other side, so I get precisely this term. And now we all know from linear algebra or wherever that I learned this from Volker Mehrmann in Berlin, that the derivative of the inverse has precisely this form, and so we get d by dtp. And so what ends up here is b times g, and g is kind of this. So I've divided by t, and let t, divided by delta, and let delta go to 0, so I get psi of this. And now the funny bit is, this flux here, n times the flux, I can actually express with my slip surface. It's precisely the slip velocity times the orient. I mean, just believe me at this stage maybe, but you can express this very, very easily from the slip trajectory. So the point again is that I can actually express the dynamic equation for Q conveniently with these quantities which I can compute from the slip surface, but I could not easily compute if I had time-indexed the dislocations themselves. Because, I mean, if I have a bunch of dislocations indexed by time, how do you take the derivative? I mean, it's not the linear derivative, it's some sort of geometric derivative, right? So, I mean, it's the velocity of the flow. So how do you relate a dislocation here with a dislocation there? I mean, there's a way, and I will say something about this at the very end, but it's not straightforward. Whereas in the space-time approach, it is straightforward. You can just compute this easily. Okay, and then also, as usual, I'm asking for plastic incompressibility here. Okay, and this precisely means that, I mean, here in this formula, it just does the sanity check. We usually want the determinant of Q being 1. This translates for this equation precisely the trace of this thing here being 0. And this is exactly the definition of glide motions, only no climb. So, I mean, the point I'm saying is, if I give any equation, one should always check that it satisfies the basic laws we all believe in, otherwise it's a bit fishy. But it does at least for that one. Okay, so now I can tie this together to some sort of model. So what are my variables? I've got the total deformation with positive Jacobian. I've got the plastic deformation, which has determinant 1 everywhere. And I've got my slip trajectory, where if I take these slices, I get the dislocations back. The energy functional I'm using is the elastic energy, plus some core energy, which penalizes the length, so we can think of that as some sort of surface tension. It's actually very well understood that you should get this. So it's effectively in some works by, I mean, it's a number of works, but let me mention by Conti and Ortiz, and there's a few works in that direction where this is a precise thing as a kind of a relaxation or of the line tension energy for that. So this is fairly well believed. And then finally, there's some external loading here, which comes from an external thing. For the dissipation, for this talk, I'm just going to use the variation. In general, this is a bit more complex because the lattice deforms. So you have to kind of see how many bonds I'm cutting in the already deformed lattice. So it's a bit of a matter that has to be taken carefully. But let me, for this talk, just assume that this is roughly the same. And in fact, later, I mean, one big part of the proof is to prove that they estimate each other from above and below under some reasonable assumptions. Okay, now what I do is I need what I call the forward operator. So you have a Lipschitz trajectory, which has these, which goes from t to t prime. And then I just say, well, I can think of this operationally as taking t and giving me t prime. So it's like what happens to t when I apply this. And the same thing I can do with p, which is the plastic distortion, but now it's some sort of solution to some pointwise ODE and so on. One has to prove that it satisfies the good properties. Okay, and so the way I'm formulating now the full energetics for dislocation driven by, plasticity driven by dislocation motion, I'm using a variant of the Mielke-Tile rate-independent theory. First of all, because it is a rate-independent system. All the equations I've written down are rate-independent. Second, well, the energetic theory has the advantage that I don't need to write down derivatives of energy functionals, which is quite good because my energy functions depend on very complicated quantities, right? They depend on these currents, so it's not totally clear. And yeah, anyway, so it gives me that I'm using this framework, so it has a few conditions. So first is the stability condition, which tells me that if I'm sitting in a state, I can go to any other state, but I'm already sitting in the best state, taking into account the dissipation it costs me to go over there. So maybe I'm slightly lower over here. Maybe there's some sort of warping in the floor. So I'm lowering my potential energy, but it costs me some dissipation to walk over there. So maybe it's actually better to stay here in the total function. So this is what you have. The energy at each point is already less than the energy I could have to by moving with my dislocations along to a trajectory, taking into account the dissipation. So maybe one point here is that really the fundamental degrees of freedom of this system are what I can do with dislocation motion, right? I mean, I'm not allowing movements of p kind of independently of dislocation. So I mean, the only thing I can do is I can move by dislocation motion. This is a single crystal with discrete dislocations, I should have said. And then the energy balance tells me that the energy at time t is the energy at the beginning minus what I've dissipated, plus or minus what, depending on how you set it up, what I've come in from the external forces. And then finally, of course, there's a third condition, which is new here. I also have the plastic flow. I mean, it turns out that this is a rate-independent system, so it's invariant under time rescalings. I mean, this one is clear, but here, this needs to be proved, but it turns out to be true. Because the way G is computed, there's an area factor coming in there, so it has exactly the right invariance. Okay, and so then you get this existence theorem that under reasonable, whatever that means, assumptions. So I have a polyconvex energy, a convex dissipation, finitely many Burgers vectors, and some admissible initial values. You can prove that an energetic solution exists for at least some time. It actually may blow up in finite time because that has something to do with the fact that the coercivity in the system can decay, which basically is happening when you have a rod and you make it thinner and thinner, and then it can kind of rip in finite time. And how do you compute? How do you prove it? So the standard, so it starts from a similar scheme as is classical in this energetic theory. So you have a time discretization. You have these coupled minimization problems at each time, which in some way brings me back to my roots. It's when I was Alex Mielke's diploma student many years ago, I guess. But then you kind of pass to the limit with the time going to 0, and now you and then you can pass to the limit and get an energetic solution. And what is important here, I want to stress this. There is one really kind of technical step in the limit passage. The limit passage is that I need to show stability of the limit process with respect to all kind of possible deformations. And the problem I have is that I get these time discrete problems, but I mean, how do I translate a limit kind of deformation of dislocations into something for the time approximate problems? And what turns out to be the key is you need to transform some weak star convergence into a deformation. And that's exactly what I showed you before is this equivalency. So you have this weak star convergence, but it's actually better than that, according to this theorem. You can kind of realize this weak star convergence as a deformation. And that's really a crucial ingredient to pass to the limit from the time discrete to the thing. Okay, I think I'm out of time, but yeah, I had something else to say, but I think I'll have to skip over this. So I leave it. This is more of a PDE approach to the whole thing, where you can actually do it more in a PDE way for this, but I'm afraid I don't have time about this. So I end for this. Thank you very much.